talk to you about building resilient systems in the face of production chaos, aka hunting dragons. Before we start, let me tell you a little bit about myself. My name is Renette. I'm a technical lead at Intellect, currently working on a project at Standard Bank in the digital platform space. I love reading, especially fantasy books, playing board games, and the fluffy black lady on the screen is my real boss. She doesn't approve of me being here. I'm supposed to be at home dispensing treats and cuddles. So, what is this talk about? We all love writing code, and getting into production is cool. Production is a great place to be. But what about actually running it in production? Today, I hope to equip you to slay some dragons when they start burning down production and to make your systems more resilient. What do I mean with resilience? Resilience is not about not having problems. You're always going to have problems. There's always going to be issues. The idea behind resilience is that your system should recover by itself, and if only one component is effective, the rest of the system should keep functioning with minimal impact. For example, if the system that generates bank statements is unavailable, you probably still want to log into the app and do insurance things. I'm going to tell a story that I think many of the people in this room can relate to. It's early in the morning, you're asleep in bed, having some awesome dreams, when you get a phone call or some sort of alert. The news is dire. There's dragons about. Time is running. Management wants updates every 5 minutes. Our customers are blowing up social media because apparently they never sleep. And you know, if this goes on much longer, then my broadband guy will earn his bonus this month. So what I'm going to be talking about, first of all, I want to give you some tools that are going to help you find a problem, very much related to Daniel's observability talk, if you attended it in the previous slot. Then looking at reproducing the problem, because we can't always fix it, and sometimes we have to prove that we actually fixed it. And lastly, because prevention is better than cure, we're going to look at some high-level patterns to prevent these problems. Warning, this talk started out as a Java talk, so some of the screenshots and examples might be Java-specific, but the principles are applicable to any language and any runtime. First of all, finding the problem. Our one-stop shop, the Swiss Army knife of observability, is our application performance monitoring tools. If you don't know the big words, you'll probably know some of the examples. These are things like SolarWinds, Dynatrace, AppDynamics. There's many. I'm sure you've seen a few on the screen. If you need an APM, but cost is a concern, there's also some open source options like Code. So if the examples didn't enlighten you, let me just explain quick. APMs are all about a real-time performance monitoring of your servers or containers, things like memory usage, disk usage, I/O, things like your application. How does your application threads look? How does your application's memory utilization look? How does your application's overall performance and error rates look? And then individual transactions or endpoints in your distributed architecture. It hopefully gives you alerts when things violate baselines, auto-detected or once you set, or in some cases even AI detected. And it helps you visualize the data. Data doesn't help us if we can't actually see it and use it. So that's APMs. One-stop shop, first place you go when anything goes wrong. Sometimes they aren't enough, and then we might want additional metrics. So what cases would that be? If you want to monitor third-party systems, while the APMs tend to have amazing integration for our own code, the things where we own the source code and we deploy the artifacts, when we've got some third-party tools in our stack, maybe a load balancer or a reverse proxy, the APM might not know what to make of it. Remove blind spots. If you realize there's parts of your system that you can't see, then you can use additional metrics to gain that visibility. For example, we had an issue a few years ago where we thought we had issues with the database. DBAs denied it. And we realized after a while, after looking at lots of debug logs, this problem was actually in how we pull database connections, but we couldn't prove it because we had zero visibility. So what we did, we added Prometheus and Grafana and all of that to get that extra visibility that we were missing. You will notice more problems, but those problems were always there. You just ascribe them to cosmic bit flipping or something. The cool thing I find is that it's super customizable. You can add your own custom dimensions to things or aspects of your system that your APM might not be aware of. And you can add metrics for anything. If there's anything in your code, even if it's specific business logic that you want to know, how many people are actually using this feature, you could add metrics for it. And lastly, redundancy is good. You don't want to land in a situation where there's a crisis, everything is down, and you can't get into your APM because, I don't know, there's a network issue between your services and the SaaS APM sitting somewhere else. So, in our metric system, if it is separate from your APM, it doesn't need to be. You would have some sort of metric store like Prometheus. It's got a time series database where it actually stores the data. It's got a service discovery mechanism to actually discover the targets it needs to scrape, and then it scrapes them, generally using a matrix endpoint components exposed, but there's also newer integrations that use push models. And it also scrapes third-party applications, and then you visualize it using Grafana. So that's metrics. The third tool we've got in our toolbox is very similar, and this is distributed tracing. The idea is now, instead of looking at an individual component, we want to look at the data flow across everything. The idea is to visualize requests as they flow through a distributed system. Whether you've got microservices or a plain old service-oriented architecture, very few of us have the luxury of working in an isolated system. So you need to see the bigger picture. The idea behind distributed tracing is that if you've got an application set up where you've got microservice A that calls B and E and B that calls C and D, it gives us a hierarchical view on the right side to show how much time is taken in every single component. Some tools that's available for you, once again, if this isn't already in your APM, it might be. First one's OpenTelemetry. The idea behind OpenTelemetry is that it's vendor neutral. It's all about collecting the data and pushing it somewhere. That somewhere can be one of multiple things. Then we've got two older tools, Zipkin and Jaeger. They're from Uber and Twitter, respectively. They do both collection and combine them with analysis or visualization. But if you choose to use the vendor-neutral way, you can combine them with OpenTelemetry. The major cloud providers obviously also have their tracing options. AWS has X-Ray, Google has CloudTrace, and in Azure's case, it's built into application insights. Like I said, this could be in your APM already. You don't always need a separate system. There's trade-off and obviously cost aspect if you deploy more things. This next one's pretty boring and sounds kind of self-explanatory, but logs. They're boring, but they're probably the most important thing and very helpful if you do it right. First of all, use your log levels appropriately. Don't log everything at error level if it's not an error. Log things at debug level when they're debug, but don't log nothing. That's almost as bad as logging too much. Correlate the logs. If a request starts on microservice A and ends on microservice D, you kind of want to know that they belong together. Make them searchable. The last thing you want to do at 2 a.m. in the morning is SSH into 20 different servers and grab those logs until you find the error you're looking for. And hopefully it hasn't been rotated by then. Include important context. Don't just say something went wrong or this input is invalid. Say this input is invalid, here is the invalid value, or something went wrong, an exception was thrown, here is the stack trace. Include important context. And then this one is a bit of a niche one, but it's extremely helpful to be able to change your log levels without restarting the application. If you're debugging a weird issue with a connection pool that's leaking, you know for a fact it's going to stop when you restart the application, and you won't be able to reproduce it, but you do need to fix it, because otherwise it's going to happen again next month. The perfect storm does happen. If you think something can happen, it will happen. So fix it. The two next things we're going to look at is a little bit more situational. The first one is thread dumps, or sometimes called stack dumps. And it's a snapshot of the state of all the threads of your application process at a specific point in time. The context where you want to use this is your server application has become completely unresponsive. There's some exhausted thread pools that your APM is yelling about. You've got stuck threads or deadlocks. A lot of the time, these are also like, APM goes like, there's a stuck thread, can't help you more. And go like, okay. If you've got some sort of bottleneck or high thread contention, and if you've got high CPU usage for an inexplicable reason, like bad regex, happens to everyone. So when would you do this? Well, first prize is during the incident. A lot of the time also while you're busy debugging something or trying to reproduce the incident. And then you can take a few ones frequently over time. If you notice service is degrading, you take it a few over time and compare them. So how do you do it? Some of your APM tools, when they instrument your applications via an agent that's dynamically loaded, they might be able to do it programmatically, either built into the language or importing some sort of profiling library. Language-specific tools. In Java, we've got JStack. In the .NET world, there's .NET Stack. Some operating system tools on Linux are also available for profiling, but I would stick with the language-specific ones if you can. They provide better context. Once you get that thread dump out, it's a big-ass text file that looks something like that. Now, unless you've only got a handful of threads in your application, I wouldn't recommend trying to read it. You need to analyze it somehow. That could either be an online tool, the specific one comes from fastthread.io, or your IDE. Most of the JetBrains IDEs, VS Code, Visual Studio, all of them can analyze this data. And what you want to look at is, are there threads that's all blocked by in a similar set of code, locked on a similar lock, waiting for a specific code? In this specific case, it was a performance issue, and you can see here it was blocked on the very specific get slow method. Very creative. So that's thread dumps. The next tool I want to talk about, and this is the last one we're going to talk about in terms of identifying the problem, is memory dumps. So very similar to what we've just seen, except it's for your allocated memory instead of threads. And before I go on, there's something I need to clarify. Even if you have a garbage collector, you can still have memory leaks. I promise. I have had many of them. So what a heap dump, sometimes called a GC dump, or just a memory dump or memory snapshot is, it's like the name implies, a snapshot of all the objects in your process memory at a certain point in time. Why would we need it? Well, the aforementioned memory leaks. If you've just got inexplicable high memory usage, or when you run out of memory, whether it's due to a memory leak or something else, you might want to know what is eating up my memory, or just weird garbage collection patterns. Maybe your application is spending a lot more time than it should be on garbage collection, and you want to optimize it. When would we do it? From here on, things should kind of sound similar. during an incident, while you're producing or debugging, and frequently as performance degrades to compare. One careful thing here is if you've got a huge amount of memory allocated to your application and you run out of memory, but you don't have enough disk space to save that memory dump, good luck. So, the how's, once again, pretty much the same. APM tools, you can do it programmatically. Like I know in Spring, you can even expose it as a HTTP endpoint, which is convenient. Some language-specific tools. In Java, we've got JMap. .NET has .NET dump and .NET GC dump. If you go to your IDE, it's got probably got tools for JavaScript. And yeah, most languages have got their tools. And then once again, you analyze it. My experience, good analyzers for memory dumps are a lot less common than good analyzers for thread dumps. So find some resources for your language. This specific one is for Java. It's called Eclipse Memory Analyzer. It's very helpful. It generates this report for us, which goes like, here is where I think the leak is. And while it's not 100% accurate, it tends to be pretty good. So now we found the problem. There is definitely a problem, but we don't know if our fix actually works. So we need to reproduce it. First thing is obviously load testing. How does my system behave when I throw a shit ton of load at it? The idea when you do load tests is don't just start up the app and put load, right? Think about it a little bit. We want non-idle circumstances. Production doesn't break when everything around it is working. We want it to be close to production, both in terms of the allocated resources and what you test. We've had cases where we run a load test, go like, yes, this code is ready for prod, deploy to prod, and then it breaks. Because turns out the things we were load testing wasn't actually what was being used in production. Before you start, figure out your goals. What is the information you want from this load test? Do I want to know how far I can push my system? Do I want to know if it can handle a certain load spike? Do I just want to know if some other components behave? Look closely at your results. So many times, great, I've done load tests, my response time looks amazing. Neglecting to look at the error rate that was sky high and some circuit breaker tripped, so response times were quick, but it was 100% error rate. That doesn't help. Be proactive. Don't just wait for load testing until you have a problem. Do it when you're doing major upgrades, building major new features, rolling anything out to prod. And while you're doing this load test, look at all your other observability tools to make sure your system is behaving as expected. The thing is, this isn't easy. The biggest, most important thing of load tests is you need to somehow mimic your production environment. And that's hard, especially if you're still running on-prem, not containerized, nothing very dynamic, because the scale is different, both of your application and downstream applications. Data. Say we've got a beautiful little cache that caches things for every user. That means I can't just run my load test with one user. I probably need to run it for thousands of users to mimic production. The network in the testing environment always behaves, unlike the one in production. And we've frequently done load tests where we bring down other systems that weren't supposed to be part of the test. So you can look into solutions to mock out those downstream services, but obviously that has some downsides because now your load test is once again further from production. There's many different tools available out there to do load tests. I just want to highlight 3 of them. The first one is kind of old but good, Apache JMeter. Not very pretty, but once you know how it works, it works. This is the one I tend to use just because I'm familiar with it. Then people went like, hey, wait, what if we put our load test as code and commit it to Git? Great idea. So then Gatling became a thing. It's a little bit clunky, but the idea is that your load tests are now written in Scala. It's got both the open source and the enterprise version available, and the enterprise version obviously got a few more bells and whistles. Then a new kid on the block, kind of Grafana K6. So this is Grafana's load testing framework. And the cool thing is they've got your tests are written in JavaScript, so once again code, and they've got a pretty good DSL going here with not too much noise. So you can actually focus on the test. They've also got some very nice web dashboards to see how your test is actually behaving. Important thing to remember though, this is how your test is behaving. You still need to observe how your application is behaving separately. Then that thing I said about the test environment's network usually behaving, sometimes we need to add some tame dragons into the mix. This is not a talk about chaos engineering. I just want to mention one tool, and that tool is called ToxiProxy. It's from Shopify's chaos engineering tool. And the big thing is it allows you to simulate all kinds of interesting network conditions. It's got a proxy that you start up, and then your applications go through the proxy to whatever downstream services you have, and the CLI, which allows you to change the proxy on the fly. It's got a bunch of different deployment models. You can have it run in Docker or some sort of native executable. And it can do things like add extra latency, limit bandwidth, delay socket close connections early, slice TCP packets up smaller, or simulate TCP resets. So that's all about reproducing the problem, but we would still like to not have been woken up at 2 AM in the first place. So how are we going to prevent this? The first one and the biggest one is, if you take anything away from the stalk, it's this. Put timeouts everywhere and make them as small as possible. When I say everywhere, I mean everywhere you're doing I/O, whether it's HTTP calls, database connections, message brokers, anything everywhere, and put them as close to the network layer as possible. If the customer is going to get an error message anyway, at least I could get an error message quickly. The next one that's also such a small thing that makes a huge impact is connection reuse. Connections tend to be expensive to make, so this is the one real case where it actually makes sense to reuse objects. So it improves the response times on very chatty services we've seen where it makes a lot of outgoing calls. Just reusing HTTP connections can drop response times by almost 50%. It improves resource utilization because now there's not that constant overhead of allocating memory and garbage collecting and allocating and garbage collection, and also on your actual connections on the operating system level as well. It helps reduce the snowball effect. When DNS is wonky or there's a network hiccup, suddenly instead of a massive spike, you will only have a small spike because most of your connections were already open. And because of all of these factors, it helps improve the resilience of your system. So where is this supposed to happen? Once again, everywhere you can. The most common one is database. If you read up about connection pooling, 90% of the results are about databases, so it's sometimes hard to find resources about other situations. HTTP connections. Use HTTP 1.1 or HTTP 2 instead of HTTP 1.0, which unfortunately many HTTP clients default to the older ones. When you have connections to message brokers, when you've got reverse proxies or layer 7 load balancers in your stack, those tend to be single points of failure that take a lot of traffic, so focus on them. And yeah, basically any network components you have. The third prevention tool we've got in our toolbox is circuit breakers. This once again goes back to the idea if you're going to fail anyway, fail fast. The principle between circuit breakers is this. Between your client and your downstream supplier, you've got a circuit breaker. And this thing monitors if calls are successful or not. If there's a bunch of successive timeouts or failures, the circuit breaker trips, and for a period of time, requests are rejected immediately instead of passing them down to the supplier. The request is failing fast instead of timing out. It prevents resource exhaustion because there's a bunch of threads here waiting for connections. It helps us recover gracefully, hopefully, and helps reduce pressure on the supplier so the supplier can also get a little bit of peace to recover, hopefully. The next one we've got I find a little bit less familiar, and that's bulkheads. If the dragons are burning down one tower of your castle, maybe install some fire doors so the fire doesn't spread. So the idea is to isolate parts of your application. The concept originally comes from ships, where the bulkheads, if water is entering in one location, it isolates that location. But we can apply the same thing to our applications. And we do it by limiting the number of concurrent calls that's allowed to a specific method. And in that way, similar to circuit breakers, when a downstream component fails, because, we built amazing systems, our things would never break, right? We can limit the scope and how much it impacts us. So if you've got the microservice A that looks something like that, it's got two downstream suppliers, X and Y, and we've just got the shared connection pool to them. What this means, if X starts misbehaving and slowing down, we also won't be able to make calls to Y because the connection pool is exhausted. Instead, we're going to separate them out, and if X starts slowing down for whatever reason, features that only depend on Y will be unaffected, and our customers can continue with hopefully limited functionality. And when I talk about limited functionality, the next tool in our toolbox is fallbacks. When there are errors in your system, if they are not critical, then let the customer continue doing things. So, like I said, ignore non-critical errors. Obviously, you can't ignore anything. Probably, if the authentication system is down, there's no sensible fallback to get the user into the app. But like I talked about earlier, if other components are down, continue as much as possible. Default to an alternative code path, it could be some sort of default value, a different source system, or even a cached value. And allow the customer to continue with limited functionality. So, wrapping up the talk now, unfortunately, there's no silver bullet. I've given you a bunch of tools, but you have to know your system, understand your tools, understand your data, and most importantly, build a culture of constant improvement. When something fails, investigate it, fix it, make sure the same thing doesn't happen again. I can tell you, one of the worst feelings in the world is having 2-3 months in a row, every single month, the same thing break. You're like, oh yeah, the same thing broke last month too. We know about this. So, that's my talk about dragons. I never thought I would talk about a tech conference about dragons. Please leave feedback. And yeah, any questions?
We're talking about fallbacks. How do you approach the difference between a safe fallback and bimodal behaviors, which aren't always well tested?
Unfortunately, that's wrong a lot of time. If you don't know whether the fallback is safe, I would say rather don't do it. All right. So it's a tricky one because a lot of the time, people do fallbacks where we're going to assume there's one thing, and then some other system takes that data and persists it, and then you've got inconsistent data, which creates a hell of a mess. So you have to know your system well, and if you don't know whether something is a safe fallback, then rather don't have a safe fallback. But the key thing is, no other system should take that data that you fall back to and assume it's true and real.
You spoke about circuit breakers, and you said you can switch off certain features, let's say in your API, if a downstream service is down. How would you go about achieving that?
Look, so generally I would say find a library that does it already. There's many out there, but generally it's some sort of stateful components where it goes like, in the last minute I've had so many successes and so many errors, and this breaches a certain threshold, so now I'm gonna be open for the next 5 seconds or something.
Thanks again for your talk. Just speaking about bulkheads, so we have this sort of, I guess, optimization problem between reusing connections and then bulkheading them. How do you approach that?
Okay, so first of all, there's a few things to remember, right? Connection pools aren't the only way to do bulkhead, right? That's one convenient way. You could also look at something like semaphores or thread pools. And secondly is generally when connections are pooled it's connections between two hosts, right? So if your two downstream suppliers aren't sitting on the same host, then we can't reuse those connections anyways. So then it doesn't really make an impact. But yeah, like it's always a trade-off you have to make, right? We've also had cases where our observability tools bring our application down, which is not ideal, because so you want to find that balance of enough but not too much. Thank you for coming, everyone.